All right. Hey, everyone. It's great to speak to you all today. I've been giving a talk like this at CVPR, it seems like, for almost 10 years and sharing perhaps the same message every year. And what's exciting me today is that after all these years, it feels like we are starting to see some of the results that give the substance behind the vision that we've been sharing, that end-to-end deep learning will be the way that we are able to bring autonomy to scale safely. So I'm pretty excited about that. And today, looking forward to sharing with you a number of some new results that actually we're sharing for the first time today. But I start off with this image, which is actually taken from a new data set that we're excited to release today, because for me, it really epitomizes the complexity of the physical world we live in. And if we're truly to get the benefit of being able to interact with and benefit from AI in the physical world, we're going to have to build systems that are able to deal with complex environments like this here in central London. So I'm going to talk about the road to embodied AI today. And of course, science fiction has some of the best depictions of embodied AI from, you can pick your favorite, from C3PO to Marvin the Martian and many others. But what's common among all of these characters is that they have the intelligence to understand scenes that include very open-ended kind of scenarios. They have the ability to understand language and build a sense of a relationship and trust so that we can delegate tasks to them. And that's very much very much what I think we need to be thinking about how to build. How do we build systems that have the onboard intelligence to be able to delight us and for us to be able to trust, delegating tasks to them? An argument I'd love to make is if we take a step back and over the last decade and look at where the frontier of AI has been, it's been interesting to me how it's moved from different fields, from perhaps vision to language to where I think we're going to be going next. It'll all be about embodied AI. Why is that? Well, I think I'm a big believer in problem-driven research. Problem-driven research, I think, motivates some of the most bold ideas. And in particular, in machine learning, we've seen this recipe that a clear, a vast data set and a clear metric or benchmark or simulation system, these things is a recipe for just incredible innovation. And of course, that started with ImageNet, giving rise to everything from batch norm to ResNets. I think language, of course, recently has taken the cake with the enormous scale we see with text tokens and training. But what I believe is going to come next in autonomous driving is we're now seeing the ability to build truly world-class simulation systems. The scale of video data is orders of magnitude ahead of, and perhaps more open-ended than where we see, language or even sandboxed data sets like we've been dealing with in the past in computer vision. And I think coming into the open domain, and more importantly, the motivation to find a truly fundamental solution to the AI safety problem, I think this is what autonomous driving and, more broadly speaking, embodied AI can offer. So let's dive in a bit deeper. Before we do, I'm just going to really quickly talk about the work that we've been doing at Wayve. And look, these slides haven't changed in the 10 years I've been speaking at these workshops. But of course, we've heard a lot today about the what some refer to as the classical approach to autonomous driving, but where the problem is broken down into different parts, many of which, of course, use machine learning today. But people often ask, are we really one end-to-end network? And it's actually the case. At Wayve, we have built one single neural net that goes all the way from sensory input to trajectory output. It's a holistic neural network that's completely data-driven, learning how to understand the world and interact with the world. And I can, of course, show driving videos all day long, but here's just an example one from the other day in central London. As you can see, our vehicle coming up into a busy, unprotected right turn. Now, this car does not have an HD map. It does not have any LiDAR. It's, in fact, a camera-only vehicle that is able to learn how to cyclists pass us, yield for them, pull in, and actually figure out from the visual scene which lane it needs to be in, how to navigate into this far lane due to the roadworks, and to do all of the multi-agent navigation required to get through that complex environment. Just one example, but if you're interested, there's many more on our website. The promises of an end-to-end system for autonomous driving are many, but some of the more interesting ones for me are these four. The first one is perhaps less talked about, but end-to-end offers a much more portable system between compute devices. And that's because it's computationally homogeneous. It's built from building blocks of neural network building blocks, but essentially it's a very streamlined, easy to optimize forward pass of a neural network. There's no multi-threaded different microservices that need lots of communications to go between them, but it is a very, in many ways, simple inference task. Of course, being able to generalize through data means that we can scale with a bit more experience to adapt to new scenarios, new vehicles, new sensor types. Ultimately, we want to build the most embodiment agnostic representation, and end-to-end learning is the promise of being able to develop a system that can learn what it can or can't see and how it can understand the world. Scalable and economic, of course, reduce the dependence of significant sensing stacks or HD maps, but I guess most importantly, produce the most safe and performance systems. We've seen this story time and time again, that end-to-end learning can outperform hand-coded rules, and there's nothing different about the embodied setting. So with that introduction, today I want to talk about three things that I'm really excited about, our whole team is excited about, and this is the culmination of so much work behind the scenes. So I want to give a huge shout out to all of our team that have made this possible, many of whom are here this week. So please come and say hi if you want to learn more, and I hope this can be the start of a conversation about some of the work we're doing in Embodied AI. But for me, these are three front of mind topics that we're going to deep dive: simulation, multimodality, and scale. So let's dive in. The first one on simulation. How about this as a title? End-to-end simulation for end-to-end driving. Well, today we're excited to talk about a new approach to simulation that we're releasing. But let me start off with by zooming out and looking at what are the outcomes that we need from simulation. Well, there are many different approaches to simulation that we've seen today. I've got four examples, but there are many, many more than this, from our Ghost Gym system to Waymo's simulator, of course, the open source Kala, Wabi World. There are so many, many more. What do we want to see from a simulation system? Well, I think the five key things to me are: we need to be able to close the domain gap, not just crucially in perception, but also behavior. We need to be able to simulate the complexity of the scenes we live in. Of course, the edge cases are often when you get car doors opening or debris on the road, and we can't just simulate rigid body actors, but it's really the deformable complexity of the world that becomes important here. Crucially, it's not just about rendering the environment, but actually simulating the full embodied platform, the latencies, all of the artifacts that come with running a full embodied stack. It needs to be data-driven and scalable. And again, going back to the title of end-to-end simulation for end-to-end driving, I think the same story we're seeing play out everywhere will be true in simulation as well, is that an end-to-end learn system will let us scale. And then finally, it needs to be controllable so that we can produce adversarial examples, we can simulate the long tail and things like this. Okay, so what I'm excited about today is that I think for the first time, we are starting to introduce a simulator which addresses all five of these. So let me explain how. To start off, I'm going to put together the different building blocks. So the first one is on, of course, neural reconstruction. It's incredible today that we're able to take simply video and in a self-supervised way, produce systems that can render complex scenes with near photorealistic accuracy. And we've seen this for a few years now, right? And so here's one example here in central London. So this is a base building block in such a system. This time last year at CVPR, we talked about Ghost Gym, which for us is our simulation environment that takes us as a building block, but produces a full closed loop simulator. It simulates our robot stack, the latencies, and everything we need to be able to drive in such a virtual environment. And we've been using this for some time at Wayve, and it's a really powerful tool for us. But what I want to introduce today is, of course, neural reconstruction has been for years done in static environments. We are super excited today to introduce Prism 1, which is a self-supervised system that can reconstruct four-dimensional scenes, so space and time. And here you can see some examples from either London or the San Francisco Bay Area. And again, this is a full data-driven, non-parametric spatial temporal reconstruction here. And so this can reconstruct dynamic urban scenes. And if you look at this example, one of the truly exciting things to me here is, of course, we see the thin structures, the incredible reflections in the puddles, but we also see the cyclists in front of us, the wheels turning, the feet moving, and it's incredible fidelity in a dynamic scene here that we can reconstruct. Of course, there's the pedestrians on the left as well, but our system Prism is capable of not just reconstructing static scenes, but from a single drive through here, we can replay and resimulate a full dynamic scene. Here's another example just to show the novel viewpoints that we can generate. Here, we're just driving forward with the sinusoid function. And if I can point out a number of different things in here. So sorry, we're rendering a sinusoid function as we go forward here. But this is, again, entirely simulated. You can see the complex reflections in the puddles on the road. If I point out the traffic light, you can see it turns from red to green. Again, this is a temporal factor. That's traffic lights, car lights are often not considered. And then, of course, you see this pedestrian on the right with an umbrella, which is got incredibly high fidelity in its reconstruction. The super exciting novel view synthesis. Here's another example going through a central London environment. Again, the complexity is just, if you were considering a procedural world where you were to place all these different assets, it'd be a very complex one to reconstruct. But again, a data-driven method enables us end-to-end to learn scenarios like this. So you can see here, we're controlling the time dimension. We're placing a camera in 3D space and simply holding the camera still and controlling time. And you can see how we can have some quite fine-grained control and highly realistic resimulation and rendering of these scenes. And of course, in this one, some really challenging lighting conditions. See on the right, you can see the lens flare and all of the realism that you'd expect to see in closing that domain gap. This technology is truly exciting. One of the things we found when we were developing this technology is that there wasn't really the right data set for us to benchmark or develop this and really push the boundaries. So today we're also excited to be releasing Wayve Scenes 101. This is a start of a data set that we hope can motivate new work in this space. And so please check it out if this is research you're interested in, but it covers, we really aimed for producing the most diverse and challenging driving scenarios. Interestingly, it has a novel camera that we would suggest that we can use as a held out camera to test reconstruction quality. We've got cameras that have up to 2 meters of baseline between them. So some quite novel viewpoints that allow us to really benchmark the reconstruction quality in dynamic scenes. And just to really illustrate the diversity, I mean, here's some examples from light to rain to night, or perhaps more interestingly, here's that scene I showed you at the very beginning, complex central London. And if I've seen a challenging scene to reconstruct, look at that top one with all of the pedestrians and complexity crossing this path in central London. So we're excited to see how this data set might push forward this challenge of reconstruction, and is what we found really useful in helping to develop Prism 1. So Prism 1 is the rendering engine within GhostGym that allows us to render complex dynamic scenes. The fifth aspect that I described that's really a really important factor for simulation is, of course, controllability. And so I want to just touch on how we can use generative AI and other techniques to build on top of this to actually have more fine-grained control in the simulation scenarios. Firstly, I want to just recap GAIA, which is this time last year at CVPR, a model we introduced. It was really the first scaled up world model that we produced at Wayve. It was a vision language action model that allowed us to take images, actions, text, and code them into tokens and run an autoregressive model to be able to predict the future and render this in high quality video. And we've got a full paper now published if you'd like to read more, but there's a ton of work in this space. And I'm so excited about world modeling because it offers a natural self-supervised task to build a really robust representation and this figure just shows it's from one of these surveys that I'd recommend you read if you want to catch up on the space. But from the work Mile that we published a couple of years ago to GAIA to many others across the ecosystem, this is just an exploding space right now, which is super exciting. But here are some results from GAIA. Now, unlike the previous work I showed, which was simulated scenarios that was re-simulating environments that were driven through before, these videos are entirely created from scratch. They're synthetically generated, and you can see that we can control the weather, the day, and we can prompt this system and ask it to create a video and prompt it with an existing image we want to simulate forward from, or even just from scratch, or with a text prompt, or any combination of the above. But I wanted to talk about controllability. And so some of the capabilities GAIA offers is we can actually prompt the system. In this example here, we can force the ego car to drive to the other side of the road and create an edge case. And then you can start to simulate forward how we will interact in that scenario. And this is just an example of being able to control and create an example of an edge case that we may want to learn from in a safer way than, of course, we wouldn't want to see this in the real world. To give more examples, we can even use GAIA to build on top of Prism, which I just introduced. And so here you can see an example where we can prompt GAIA to render a vehicle within, for example, a cuboid, or we can point to a part of an image and ask it to create additional content. For example, here putting a vehicle, or here a bus, or two more vehicles. And now this is an interesting example on the bottom where all of the dynamic agents in this video are synthetically generated by GAIA on top of a neural rendering, on top of Prism. Now, the thing I'd point out here is if you look at the sedan that drives past us on the right, we've got two novel views here, and you can see that it's consistently generated between those views. I think that's a really powerful demonstration of controllability of the simulator, because we can add content on top, and it's coherent both temporally and spatially between these different sensors. And the final example I'll give within Prism is that we can, of course, remove and modify dynamic actors. And here you can see an example of a pedestrian inserted or deleted here, crossing this pedestrian crossing scene. You can also see, of course, there's a complete full dynamic environment with the traffic light changing and everything like this. So I guess just to sum up this section on simulation, what really excites me here is these are the building blocks of what I believe is a full data-driven simulation environment, GhostGym, that allows us to train the system in a data-driven way, control and create and understand edge cases, and of course, simulate the entire end-to-end stack, including the embodiment and the world jointly. I think this is the kind of tool that will be able to be scaled up. As an arms race, of course, if you solve simulation, you solve self-driving and vice versa. But as we scale up our data-driven driving stack, scaling up our data-driven simulator will be a corresponding task. And I'm really excited for these things to grow and for the possibilities that it's going to open up for our learning. Awesome. Let's talk about multimodality. So second of the third areas I'd love to deep dive. Multimodality has, of course, been a huge focus of the AI space recently. And I want to talk in particular about vision language action models, grounding driving or embodied robotics with language. This is something we've been working on for, I think, almost 3 years now. And at the start, a lot of people were asking, why is language important for driving? One of, there are a couple of really key reasons here. Firstly, multimodality, of course, opens up many more sources of data to be able to learn from, not just, say, driving data, but of course, the broad diversity of internet scale text data. This opens up the possibility of learning more understanding about human values, common sense, other contextual reasoning that might go above and beyond the data we see in video or driving. Of course, it also creates the possibility of interaction and actually building a relationship or debugging or understanding how our vehicles are reacting. And that opens up a ton of interesting features for self-driving. So this time last year, again, just to recap, we introduced Lingo 1. Now, Lingo 1 was a vision language action model that was able to do offline visual question answering. And it was an interesting system, essentially using, we took video data, we were able to encode it, and pass it into a language model, which we were able to fine tune alongside text inputs, fine tune it to output language about the driving scene. And we could, of course, keep feeding this in and have a conversation with such a model. Now, the interesting thing about this is that it was able to learn language understanding that was really grounded in the visual scene. And to show you some of the results, you can see on the left here, Lingo 1 was capable of commentating. Here you can see it's slowing down due to a jaywalker. It's describing quite dynamic and interesting scenes while our system is driven through them. And so it's able to commentate in an open loop setting, as in it can just watch these videos and commentate by jointly reasoning about the driving decisions as well as the visual scene. We could also do visual question and answer. You might not be able to read this, but we're asking questions like, what do you find risky in front of us? What do you see? And Lingo was able to say, look, there's a van on our left about to pull out, and it even spots a cyclist that's secluded on the right behind the vehicles. We were also able to demonstrate referential segmentation. And what this means is that Lingo would not just talk about what it sees, but actually point to things in the image. Here we're asking, what are you paying attention to? And you can see Lingo points out A, B, and C, this free space in front of us, the car in front of us, and the traffic in the distance. And we found that this referential segmentation really reduced the volume of, say, the likelihood of any hallucinations, because it had to ground its answer in the visual scene. But let me move forward from this there. So that was last year. I'd love to introduce Lingo 2, which is our latest multimodal model here. And what we're really excited about with Lingo 2 is it's the first model, we believe, in the world that is capable of closed loop driving. So what this means is it's not only not only reasoning through language, but it's also actually driving the car in closed loop. And this is something that we've demonstrated. It's a single end-to-end trained model that, of course, takes in the visual state, text, learn queries, navigation prompts, things like this. And through a vision language action model was able to output a conversation as well as drive the car in closed loop. You can read more details about it on our blog here that we put out, I think, a couple of months ago. So here's an example. So you can see us here driving in central London, and we're talking about, so this is actually Lingo 2 driving the car in closed loop, referring to the jaywalkers in front of us and commentating on its driving at the same time. Here's another example, which is quite interesting, where it's talking about it's keeping a steady speed, but then actually recognizing there's a bus and that it wants to overtake it. This is quite a complex thing to recognize, but it recognizes that the bus was actually parked at a bus stop before coming back into its right lane and slowing down for this traffic light. Or here's another example where it's reasoning about, again, an empty pedestrian crossing ahead of us. So some quite diverse examples, and I mean, this is not overfit, right? This is these, of course, were not present in the training data. We've literally gone to the open world, driving in London. Of course, we can't control the weather or how other agents behave. And you can see the generalization capabilities that Lingo 2 has actually learned things that generalize and are grounded in a physical real world test in central London. Isn't it amazing what AI is capable of today? We can even test it further in simulation. So here you can see on the left, we've actually input a text prompt and we've asked it to continue straight or to slow down for the upcoming turn. And you can see that the driving policy changes its behavior based on the input text prompts. Or here's another one. Again, this is in Ghost Gym. On the left, we can ask it to stop behind the bus, or on the right, overtake the bus. And you can see the driving policy conforms to the prompt instruction that's fed into it. Again, if we go back to, if you remember the GAIA in painting that we talked about, in this one on the left, we've just inserted a car in front of us completely synthetically. And you can see in the bottom left with the inserted car, Lingo says it's slowing down to match the lead vehicle speed, whereas in the top left, it was increasing speed to match the speed limit. And on the right, again, we insert a car. On the top right, it says it's slowing down for the red light. And in the bottom right, it says stopping behind the stationary traffic. And so we can really start to use, I mean, this is an example of using Ghost Gym to be able to test counterfactuals and understand how our system, how the system behaves and operates in the world. Why is that interesting? Why is that important? Well, I want to leave this section with one thought, which was, I can often feel in self-driving of yesterday that when you get in a vehicle, it can often feel like you don't have much control. You get into a set vehicle, follow a set route, and perhaps these are some of the exaggerated, but perhaps some of the emotions that it might conjure up. And I think if we think about the true promise of embodied AI, if you go back to the science fiction characters as I introduced at the start, I think the real full potential of these systems is to produce a system that's much more like a chauffeur driver, one where we can build a relationship, delegate tasks to these intelligent machines, have them respond to us, let us know what they can and can't do. And I think language grounding is the path forward for this. And so one of the reasons why we're super excited about it, and it just opens up an incredible amount of product features and opportunities as a result. Finally, third section, let's talk about engineering to product. I wanted to talk about this because often, when I come to CVPR and talk about results, of course, papers I published, engineering results are never celebrated as much as algorithmic advances, and I'm sure we all feel that kind of feedback. But engineering is scaling laws, I think, are only limited by engineering. What I mean by that is that we are seeing no end to the ability to grow performance and capability with engineering scale, whether that's data or compute. And engineering is so important to make these systems a reality. And so I'd love to celebrate it, to talk about some of the ambition and the capabilities that we want to bring to this problem at Wayve and what it might mean for a resulting system. So let's talk about what it's going to take these ideas, these research prototypes, and actually turn them into an embodied AI product that can delight the world, that people can have access to. So what we really want to do, taking a step back, is build a generalizable embodied AI platform. It should be agnostic to the specific vehicle it's on. If it has different cameras or camera radar or whatever sensor setup it is, we want to build an AI that knows what the sensors can or can't see and can understand that embodied platform. Of course, we will do this by learning from the most diverse data across the embodied AI industry. The other outcome that I think is really important to be able to enable this is to be truly excellent in inference and integration. This is can often be a grind against many engineering challenges, but being able to deploy the most intelligence per flop and to be able to have a system that has a hardware, software, fully embodied AI that is, is well constructed and architected together. This is perhaps the gap between a demo and a product. And the final point I want to make is really around safety. And I think the key word with safety is about predictability. These systems should be predictable such that we know what they can and can't do. We know when we can trust them and when we can't. So for me, these are sort of, taking a step back, 4 of the key things that outcomes that we want to create through scale of engineering that will be able to build this embodied AI product. So how are we going to do that? How are we thinking about that at Wayve? Well, of course, we want to build an embodied AI foundation model. What is that? Foundation model is often a term that's thrown around, but I think one of the best definitions I've seen is it's a model trained on a diverse set of data that can be adapted to a wide range of tasks, different robots, different applications, things like this. Of course, these models really kicked off with language or language and vision, and there are many incredible examples in this space. But unlike say language foundation models or vision language models, embodied AI foundation models have unique challenges. Data is an interesting one. Of course, we can't just, if we're really talking about hundreds of petabytes of scale of data, unlike language data, you can't put it all locally on the compute node when you're training. We have to have enormous amounts of video data that we need to stream to compute nodes, where we sample and build curriculum that almost randomly can access this data across all of the petabytes. Scale of compute is a challenge. And then, of course, the embodiment, the physical world, the safety of deployment, simulation, all of these kind of things. We can't have a static train or test set. It's got to be a closed loop system that we're able to evaluate. All of these kind of things make embodied AI that one step harder. But of course, the opportunity is also one step greater. It's been exciting to see a number of foundation models start to pop up in the embodied AI space. And we're super excited to see them from of course, RT1, RT2, many of the different manipulation data sets we're seeing coming out. There are many, many examples here. And, going back to my opening comment, I really think embodied AI is going to produce, has the best chance of producing the next AI breakthroughs. So what we want to bring to this problem at Wayve is a scale of data and compute that the industry hasn't seen before. And of course, not just driving data, we are really bringing together all kinds of data from internet scale videos to other embodied other embodied experience, from humanoid robotics to domestic robotics, drones, manufacturing, of course, large-scale driving data. And one of the beauties of autonomous driving is that there are millions of vehicles out there in the world already collecting data and doing useful work, making it economic and effective to get access to this data at scale. And then, of course, the high-quality driving data that ourselves and our automotive partners are working with. But whether it's the fleets we work with or some of the compute giants like Microsoft and NVIDIA, bringing together this picture is what I think will make that promise of embodied AI possible. And here's just some examples. If you can't learn a model that understands general purpose physical reasoning from this data, then I don't know what it's going to take. I think this data really provides a super diverse and quantitative understanding of the physical world. And so bringing that together will enable a foundation model that is truly, as we're describing in the past, truly task agnostic, truly generalizable, and enable these kind of applications at scale that can deal with all kinds of different sensor input or robot embodiments, and of course, all different types of tasks, from perception to an autonomous driving, from L0 all the way to L5 levels of autonomy. The final point I want to make on, I'd love to make on engineering to product is around actually building this into a safe system for automotive. And perhaps this is, as a last point, being able to, we've spent 8 years building an end-to-end model and learning how to develop it quickly, how to understand it, and how to make it safe. And this is not a trivial thing to do. How you can create a safety architecture that can build a quantifiable behavioral or SOTIF safety case, and of course, something that's also functionally safe that can meet the needs and expectations in automotive, is not a trivial task. And what excites me about the architecture that we're building, which I'm showing here, is that we're able to achieve that while still being end-to-end, while still being data-driven. And this is an architecture that can scale all the way from L1 to L5 in terms of autonomy, from driver assistance, active safety and warnings, all the way to autonomous driving. We can learn safety features that are self-supervised and data-driven, and allow us to build an understanding of the world allow us to build a system that can deploy such a foundation model that can grow with increasing amounts of data. So that's really exciting, and something that I wouldn't underestimate as being really important to deploying these systems. So I hope that brings together a picture of some of the frontier challenges that we see at Embodied AI at Wayve. But to conclude, let me finish with these points. I really firmly believe that embodied AI will be the next frontier of AI. And more importantly, self-driving is the way to build it. It's the way to get access to data. There's a viable commercial model, and there's a really clear imperative to build this technology because of the benefits it'll bring to the world. We talked about our new simulation system and data set we're releasing, Prism and Wayve Scenes 101, and how we can build an end-to-end simulator without the need of a scene graph that can deal with the complexities of where we need to operate. We can build trust through multimodality. And then finally, and most importantly, I'm so excited to have the opportunity at Wayve now to take this technology, to take these research concepts and actually engineer them into a robust product and see this deployed throughout the automotive industry. I hope this is the start of a really engaging conversation this week. Thanks so much. We are growing our team across our sites in London, Silicon Valley, and Vancouver. If this is a challenge that interests you, I'd love to chat this week. We'll have a booth in the expo, so please come and say hi. Other than that, thank you, and I'm very glad to take any questions. Cheers.